Okay, in this video we're going to be learning about polar equations of conics. So we're going to take our three basic conics, our ellipse, our parabola, and our hyperbola, and we're going to put them onto our polar axes in polar form. We're going to come up with equations to each of these three conics. So let's start off with our ellipse, and actually with all three of these, the two of the key points we want to look at is, number one, we're going to place the focus of each of our conic sections on the pole. So remember, in polar form, our pole is at the origin of our coordinate plane, our x and our y axis, and then the positive x-axis is the polar axis. Okay, so our focus is going to be on the pole. Okay, for a parabola, we've only got one focus, so we're going to put it there. For an ellipse and for a hyperbola, we're going to put one of the focuses on the pole. Okay, we're also going to have a directrix, so each focus has a directrix. And we're going to look at the relationship between the distance from the focus to some point on our conic section, and then the distance from that point to the directrix. Okay, so we're gonna pick some point P. So let's start with an ellipse. So we've got our focus at our pole. We've got some point P on our ellipse. We could pick any one, and then we've got the point D on our directrix that's closest to that point P. Okay, so we're going to look at the distance PF and the distance PD, and we're going to look at the ratio of those distances. Okay, that ratio is going to be our eccentricity. So with ellipses, we talked about eccentricity being a measure of how oblong an ellipse is, or how close to a circle it is. The closer it is to 0, or the closer it was to 1, how stretched out it was. So eccentricity is going to be a key in determining which of our three conic sections here we're going to be graphing, okay, or finding the equation of. So if that E value, if that ratio of this distance to this distance is less than 1, then we're going to have an ellipse. Okay, if that distance, so again, P to F and P to D, if that's the same distance, if those are equal, okay, that ratio is going to be 1, then we're going to get a parabola. And if that distance from P to our focus and from P to the directrix is bigger than 1, so in other words, if that distance is longer than that distance, then we're going to get a hyperbola. Okay, so these are the three situations that we're going to get when we look at our eccentricity. So let's look at some of the equations. Okay, there's one standard form for our equations, and there's 4 different orientations that we're going to look at. So we've got our 4 orientations here, and I've only graphed, it looks like a parabola. It could be a piece of a hyperbola or an ellipse as well. But for simplicity's sake, we've just graphed this part. We've also got a directrix, and again, our focus is at the pole. We've got these equations, real similar with 2 little subtle differences. Notice, for one, that on top of each of these equations on the numerator is k times e. Okay, k is some constant that is equal to x if we have a vertical directrix, or equal to y if we have a horizontal directrix. And e is our eccentricity. Okay, so e isn't the exponential constant that we normally see in equations, and even this kind of looks like a logistic equation, but it's not. This is our eccentricity. Okay, so if we've got ke over 1 plus e times the cosine of theta, okay, remember polar equations are in terms of theta, then it's going to be oriented this way with a directrix at x equals k. If we've got ke over 1 minus e times the cosine of theta, then our directrix is going to be x equals the opposite of k. And if we switch out the cosine with a sine, if we're adding that sine, that e times sine, then we're going to have a directrix with a positive k value. And if we're subtracting that sine, we're going to have a directrix y equals a negative k value. Okay, so how are we going to use these? Let's look at a couple of examples that you're going to see as to how we're going to use these equations and our graphs. Okay, so the directions say, find a polar equation and identify the conic section with a focus at the pole and the given eccentricity and directrix. All right, our first example, they give us the eccentricity as 1, and they give us our directrix, which is y equals 2. So we've got a little sketch here. We're not gonna graph it technically. We're just gonna give a sketch. Our focus is at the pole, and our directrix is at y equals 2. So that tells me that I've got a horizontal directrix, and I'm going to have a sign in my equation. Okay? The positive 2 tells me that I'm going to be adding that sign, and the 2 itself tells me that that's my k value. Okay, so we've pulled all that just from the directrix. E equals 1. Well, when e equals 1, we've got a parabola, so that tells me we've got a parabola. Okay, so let's set up our equation. So remember our standard form, we've got k times e, and since we had y equals, we've got sine. Since we've got a positive 2, we've got a plus. All right, so then let's plug in what we know. We know our k is 2, we know our e is 1, so plug those in. So 2 in for k, 1 in for e, and then just simplify. 2 times 1 is 2. We don't need the 1 in front of the sign, so we end up with r equals 2 over 1 plus sine of theta, and we already noted it was a parabola. All right, let's look at a second example. We've got e equals 2 over 3, and we've got x equals negative 5. Okay, so our eccentricity is 2/3. Well, 2/3 is less than 1, so that tells me that we're going to have an ellipse. Okay, so right off the bat, we know what kind of conic section we have. So x equals negative 5, so let's break this down. This x equals tells me that it's going to be a vertical directrix, so I'm going to have a cosine. This minus sign here tells me that we're going to be subtracting cosine in our equation, and then that 5, that is our k value. So our k value is always going to be positive. Okay, so let's plug in what we know. So this time we're going to use our cosine formula, and with subtraction, because of that negative 5 there. And our k is 5, e is 2/3. Plug them in. Okay, when we simplify, we get 10/3 over 1 minus 2/3 of cosine of theta. Now, in order to get rid of the fractions there, okay, so we've got thirds here and a thirds here. If we multiply the top and the bottom by 3, then we can get rid of those fractions. So everything in the top by 3, everything in the bottom by 3, and we'll end up with 10 over 3 minus 2 cosine of theta. And again, we said it was an ellipse. Okay, in your notes, I want you to practice one. Example number 3. We've got e equals 5/4 and x equals 4. Come up with the equation and what type it is. Okay, one more type of an example that you're going to see. Is this. Determine the eccentricity, type of conic, and the directrix. So this time we're given an equation, and we need to come up with the e, the directrix, and what type it is. Okay, so we've got r equals 6 over 1 plus 2 times the cosine of theta. Okay, so first things first, I want to look at this first number here in my denominator. Okay, it's a 1. That's good. We want it to be a 1. All of our 4 standard orientations have 1 as that first term in the denominator. Okay, so that's good. Always check that. That means that we can look here and we can find our e value. So our e value is 2. Okay, so e is 2. 2 is greater than 1. Okay, if it's greater than 1, that means we're going to have a hyperbola. So now we just need to find the directrix. Okay, this is a plus, so we're going to have something equals a positive number. This is a cosine. Okay, if it's a cosine, we're going to have a vertical directrix, and that's x equals. So we're going to have x equals some positive number. To find out what our k value is, we look at our top. Remember, this is k times e. I know my E is 2, so if I set 6 equal to 2 times K, that means our K has to be 3. So X equals 3 is our directrix. Okay, let's look at another example real quick. Okay, same directions. R equals 42 over 7 minus 5 times the sine of theta. Okay, this one. When I look at this first term, that is not a 1. So we need to, before we do anything else, we need to make that a 1. So I'm going to divide both the top and the bottom by 7. Alright, when we divide both the top and the bottom by 7, we get 6 over 1 minus 5/7 times the sine of theta. Okay, now we've got that 1 there. So we've got our eccentricity there, 5/7. That's less than 1, so that tells me it's going to be an ellipse. Okay, now we just need to find our directrix. We've got subtraction, so that's going to be a negative. We've got sine, so it's going to be y equals. Okay, so to find our k value, so remember the top, let's go to this one. The top is k times e. We already know our e is 5/7. So we've got 6 equals 5/7 times k. Okay, if we multiply both sides by 7 over 5 to get rid of that fraction, then we get k equals 6 times 7 is 42 over 5. Okay, so our directrix is going to be y equals, don't forget that negative from our equation, and 5 goes into 42 8 times with 2 left over. So eccentricity 5/7, it's an ellipse, and the directrix is going to be at y equals -8 and 2/5. You guys try one in your notes, do example number 6, copy down this equation, and find the eccentricity, type, and the directrix. So, we talked about polar equations of conics, the 4 standard orientations, how to determine what type it's going to be, looking at our eccentricity, how to determine where the directrix is, either with the given information or pulling it from an equation.